So the second exercise that we're going to do in Excel is learning how to create a standard curve. So we need to make a new worksheet here. So to highlight, Excel creates workbooks, and within the workbook are individual worksheets. So this is kind of a way of having all of the information that you might need for a project, let's say within an entire workbook, but then there's individual worksheets for each thing that you're doing. The same is going to be true here. So this first exercise was when we were using Excel as a calculator. So that's where we did all of our work to do kind of a serial dilution. So to make a new worksheet, you just kind of come down here and you hit the plus button. So we're going to call this exercise 2. I'm going to sort of change what we have here so that it's a little bit easier to see. Okay. So what we're going to do here is create, we're going to put data in and we're going to create a standard curve. So bear with me for a little bit. I'm just going to read from the sheet here just to kind of highlight some important parts of why we make standard curves. So a goal in much of biochemistry research is to obtain data that can be plotted as a straight line. It's easy to fit to a standard y equals mx plus b equation and obtain useful data from the slope and y-intercept. And we've seen several examples of that so far in this course. Well, a general theme we'll see in many of our biochemistry experiments is how do I separate what I want from what I don't want? Another common theme is to use known amounts of a substance to determine the amount of that same substance in an unknown. So you guys did kind of stuff like this in general chemistry when you did titrations, where you're doing an experiment where there's one unknown, and then you kind of figure out a piece of information, and then you can use that information in order to kind of figure out an unknown in another system. So again, we did these all sort of out of order here. The biochemistry, the basic biochemistry techniques lab will examine methods of spectroscopy. Right now in this lab and using this Excel workbook, we're basically going to be focusing on how we analyze data that we obtain from spectroscopic methods. So how is this relevant to biochemistry? We're actually going to be obtaining data that is from a Bradford assay. So Bradford assay is a commonly used biochemical method that can allow us to determine the amount of total protein in a sample. And what we do is we base it on comparison of absorbance values to a series of protein samples that we prepare by serial dilution. So one of the things that we're going to create here is a couple of tables. And as I create these tables, I'll kind of reinforce this. Okay, we are using known concentrations of proteins to create these 8 samples that we then measure some absorbance values of. And then when we have unknowns, we can then use that data, that absorbance data of the unknowns, to figure out their concentration. So we'll walk through it as we do it here. So I'm going to have to create these tables that are here. This is all the information that's on your handout here. So we basically just need to type this information in. So we're going to have sample ID. We're going to have 10 samples. Stock volume. So we're always going to be taking 20 microliters of our stock volume. Oops, and I said 20 and I typed zeros there. So again, we can kind of drag this down here. That'll pull that in to create 20s there. If you want here, we can say that this is going to be in microliters. We can add those pieces of information in. Stock concentration. This is going to be a different this is going to be a different set of dilutions from what we had on our first exercise, where we always took the sample that we just made and that became the stock for our new solution. That's not necessarily going to be the case here. As you can see here, we're going to be just typing in this information here. I'll explain this in a second. Oops, we only have 8 samples. My apologies for that. This one's going to be 0. There we go. Now that's right. Sorry about that. Okay, so how this serial dilution works, and this is different from what we did on the previous exercise. Basically, we're going to be taking 20 microliters of a stock that is, and let's go ahead and put these units in. This is going to be, our stock concentration is going to be milligrams per milliliter, which is the same thing as micrograms per microliter. Okay, we're going to be using that stock concentration. We're going to be using 20 microliters of it. And so just like we had before, we're going to need to figure out what our final volume is. I think I typed that, final volume in microliters. We're going to have our final concentration. And again, we'll have that in micrograms or milligrams per milliliter. And then volume to add. So right now I'm going to go ahead, like we did before, I'm going to format my columns, auto fit selections, so that I can basically make sure I see all of my information here. All right, so again, highlighting what we're doing here, we're going to be making 8 samples. They're going to have a certain volume of our stock solution. Okay, the concentration of our stock solution is either given here, or note this, for sample 4, we're going to use sample 2 for that. So we'll have to come up here and get what that concentration is in order to be able to use it in our calculations here. So the last piece of information to add here is we've got the volume to add here. So this is going to be 0, 10, and then these are all 20s here. All right. So one of the things I want you to see as we have these 2 different exercises is we're going to be doing the same type of an equation, a calculation. It's literally a dilution, so that C1V1 equals C2V2. But we're doing things a little bit backwards here. Remember in our exercise we had over here, let me just kind of come back over here. We needed to use and do a calculation to figure out the volume to add because we knew what the final volume was going to be. In this exercise, and I meant to write exercise 2 down there, in this exercise, we know the volume to add. So to get the final volume, we can create an equation to do that. So that's going to be equal to the sum of each of these. Okay? Now again, to get the final concentration, we can come back over here and remind ourselves the final concentration was going to be equal to, that C2 was going to be equal to C1, our stock concentration, divided or times the initial volume divided by the final volume. So we're going to essentially use that same equation. So let's actually take and copy and paste that here just so we can see that. Okay, that's going to be our final calculation or final equation that we'll use. So to get our final concentration, that's going to be equal to my initial stock concentration, which is going to be this guy. Okay, and then it's going to be equals C2 times the volume that we're going to take of that. So the volume of the stock volume that we're going to be adding, and then dividing by what our final volume is. So one of the things you'll note for this first guy, well, we didn't really do a dilution because we didn't add anything else to it. So it makes sense that that final concentration is going to be the same. So here's where this is going to get a little bit interesting here, is now when we do our next we can actually let's take and drag this down here because that's going to figure out what our final volume is that we're going to have here. So we're going to have those different final volumes. Okay. Notice an error here. There we go. Notice this is supposed to be a 30. I mistyped that from our worksheet that we have here. That's a 30. So make sure that you go ahead and fix that there. All right, because we've got basically 20s and 40s that we have here. All right, so this is the final concentration. Okay, so now when we do this guy, it's going to be the same thing. We're using the same stock concentration, but now it's going to be using a different volume of it. So watch what happens here. This is going to be equal to our stock concentration times the initial, or the volume that we took of it, and divided by the final volume. Okay, so we're going to have that guy there. So that's now 1.5. Now for this guy, it's going to be our stock concentration times the initial volume divided by the final volume. Okay, now what we have to notice for this guy, I can't just copy and paste and pull this down because things are going to get a little bit different here. Watch what happens here. For this guy, my stock concentration is sample 2. So I can't actually select this cell because it has text in it, not a concentration. I need to actually go up to my final concentration from sample 2. So I'm going to say equals that guy times the volume that I'm going to take of it divided by the final volume. Okay, For this guy, now I'm going to be using sample 3. So my stock concentration is sample 3. Again, I can't select this cell. I have to come up here. Here is the final concentration that I made in sample 3. So it's going to be that guy times the volume that I take of it divided by the final volume. Okay. Keep going through here, but notice here now this is going to be sample 5. It didn't go 2, 3, 4. This went 2, 3, 5, 6. Okay. So it's going to be equal to that concentration, which is going to be this guy, times the volume that I take of it divided by my total volume. Okay. Equals, now this is sample 6. So now it's this guy times the volume that I take of it divided by my final volume. And now for this guy, I'll actually do a calculation for this just so you could see, but I'm not taking any of that solution. So it's basically going to be my blank. It's 0 concentration. I didn't have any of it, but let's actually go through our calculation here. So it's whatever that concentration is of my stock times the volume that I took of it divided by the final volume. So mathematically that works out to 0. Okay. So we've made this table here that has this information here. So kind of running through what we needed to do here. It says complete the table shown at right using equations when possible, which is what we did, and use it to and the associated spectroscopic data to create and determine the following. Okay, so we've created this table right here, but now we need to sort of map on some additional information. We notice here that they give us the absorbance value of these different samples. So I'm actually going to add this up here. Well, let's go ahead and do this. I want to show you something else here. I'm going to create a different table. So let's have that table be there. I'm going to copy and paste this. And now I'm going to add my absorbance values at 595 for this. So I have to manually type these in. Again, just like we had with these other ones, you can see how easy it is. I made a mistake originally with that guy. I counted that as a 20. It's supposed to be a 30. So it's always nice when we have a way to get experimental data directly into an Excel spreadsheet, because there's always going to be that concern about being able to have an accurate translation and transcription of that data into our Excel spreadsheet. So that's always a potential source of error, is if we don't enter that in correctly. But we've got 2.301, 1.851, 1.361, 1.090, 0.821, 0.579, 0.481, and 0.356. Okay, so I just got that directly from this table that's here. So again, just to have you guys understand where this information comes from, we made up a series of 8 solutions that have different concentrations.
Could you try again?
Sorry, Siri. We made up a All right, I think it's done. So we made up a set of different 8 different concentrations of solutions, ranging from 2 milligrams per milliliter to 0. So we used Excel as a calculator to figure out what those concentrations were, right? And now we went into the lab and experimentally we actually determined what the absorbance value was for these. You guys already did this. If you're watching this video at a time where we're doing this lab and we're supposed to, you will be actually gathering this data at some point where you will make these 8 solutions. You will measure the absorbance at 595 after you add a special chemical to them that will turn them blue. And we're going to use that then to create a standard curve. Okay, so what we need to do is create a standard curve with this information. So this sample that we have here, we've got the sample IDs here. I'm actually going to take, and let's do this. We need to put in what these concentrations are. I want to have all of the information sort of all in one place here. So watch what I do here. I'm going to do that paste special again. And I'm going to say values, because if I didn't, let me actually show you what will happen. If I don't say paste values and I wanted to copy and paste this, if I copy and paste, it's not finding the reference data because it's trying to use those same formulas that I have here, right? It's got formulas it's trying to put in. I don't want to have formulas there. I want to have these numbers. So when I copy this and I come over here, I'm going to say paste special, and I'm going to say values. So when I say okay, now it's going to put those values in here. So note what we have here. Again, I've got the sample ID number, which is not as important as knowing that I'm going to have this concentration as a function of the absorbance. And what I need to do is I want to create a scatter plot for this, and then we're going to fit it to a straight line. Okay, so let's go ahead and do that. I'm going to select this right here, okay? And I'm going to come over to Insert, and then here's our scatter plot. Okay, so scatter plots are really important to use when you want to fit your data. You'll notice here that you can actually have, dots get connected with lines here. We're going to use a smooth marked scatter later on. You can have it connected with straight lines, but if we're going to be fitting it to a straight line, we want the only line that we see there to be the line that we create with our linear regression. So very often when we're going to be doing any data fitting, we will just use this scatter plot. So I'm going to say insert a scatter plot here. Okay. And then one of the things that we need to make sure that we check, because notice what happens here is we sort of run our concentrations run between 0 and 2, and then our absorbance values essentially run between what equates to 0 and 2.5. So our axes here both run from 0 to 2.5, so we need to make sure when we're looking at this that we didn't flip-flop and have our y and our axes flipped. So this one is set up properly. What Excel likes to have is it likes to have your x variable first and then your y variable. I'll show you how we can change this here in just a second. But I know that my 0 concentration should have an absorbance of 0.356. So I know that this is correct. Let me show you, first of all, how to change it. And then second of all, what it would look like if we didn't have this plotted correctly. So I'm going to choose new x and y values. And you'll notice here it does not include the column name heading. So when I come and I pick my x values, I'm going to pick my absorbance values now for this. And then I'm going to pick my concentration values for here. Now again, this is not correct. So let's go ahead and see what it looks like. And now we can see we still get a straight line. It looks like it's right. It looks like, oh, there's going from 0 to 2.5, 0 to 2.5. That looks like it's correct. But notice here where it would intersect my y-axis. It would say that my 0 concentration would have a negative absorbance. And we know that's not the case. Okay, so we want to have we want to make sure that our plot doesn't look like this. It still looks like it could be right, but it's not correct. So I'm just going to, my favorite keystroke, Command Z, I'm going to undo this and get back to our correct plot here. All right, so now we have our correct plot here, and we need to fit it to a linear equation, display the equation and the associated r² value. So if you select your data, and we want to show you two ways that you can do this. If you select one of the data points, and again, this is a control on Mac. For PC, it might be another keystroke. I can add a trend line, but I also want to show you where you can do it over here. Again, if we do chart design and then under add chart element, we're going to kind of come over here to be able to do a bunch of other things. So let's do that through here. We're going to add a trend line here. We're going to add a linear trend line. Now, one of the things that I like about actually using that control function is when we add, we're going to format our trend line here. We need to make sure we are looking at some of these pieces of information that we have down here. So, and these are some of your post-lab questions here. We do not want to set the intercept. You can set the intercept at a certain value. You can set it at 0, but clearly we know that we do not have a 0, 0 data point here. So we want to make sure that we're not setting that. We do want to display the equation on the chart, and then we want to display the r² value. These are two pieces of information that kind of let us know how robust our data fitting was, right? R² should be close to 1. We're pretty close to 1 there, so that's good. And this equation is important. Remember what this equation is. This equation really allows us to relate and equate an absorbance value, which is our y parameter, with our concentration, which is our X parameter. So this really is a two-variable equation. To make this chart, what we did is we used known X values, known concentrations, and we experimentally measured Y, which is the absorbance. What we're going to do now is we're going to use this equation and we're going to measure absorbance values of unknown solutions. So we're going to know the Y, and then we want to solve this equation for the X so that we can get the concentration of those samples. So that's how a standard plot or a standard curve is going to work. So this is our standard curve, right? At this point, I don't need you to know too much in Excel about how to make labels or anything on your axes or anything. So this is fine to just leave as is. But the last part of this exercise is we're going to go, and we don't have samples that we made, we're going to have unknown samples. So we've got 8 unknown samples, and I'm going to type in what their absorbance values are at 595. Okay, so now again, this is a situation where if we were able to pull this data off from an instrument directly, that would be ideal, because we're not going to then have that potential for transcribing errors, but we're going to do our best here. So 0.808, 1.341, 0.401, 0.579, 1.193, 0.594, 0.783, 0.601. All right, so those are all the absorbance values. So highlighting, let's look here. And I want to make sure we understand this standard curve. We started out by taking known concentrations. We measured the absorbance value. So we were kind of going in this direction with the creation of a standard curve. This was known. We measured this value, okay? And then that gave us, we measured our absorbance value. We had a whole bunch of different concentrations. Beer's law tells us that the relationship between absorbance and concentration should be a linear relationship. Okay, so that's what we have here. Now what we're going to do is we're going to say, you know what, now I know the absorbance value. I'm going to take, so this is 0.808, right about here. I'm going to see where that intersects the line, and then that tells me my concentration. Now we're not going to do this just kind of by eyeballing and drawing on the graph. We have an equation for this line. So we're going to use that equation now, and we're going to solve this equation for X. Okay, so that's why this equation is important. So just see what we're going to have here. Y is our absorbance. Let's actually write this down here. So Y is our absorbance. So our equation tells us that absorbance is equal to 0.9864 times our concentration plus 0.3498. That's our equation of our straight line. I need to solve this for concentration. So concentration, right, if we just do a little algebra here, is going to be equal to my absorbance minus 0.3498, right? And then divided by 0.9864. So my concentration is going to be my absorbance value, which is my Y, minus 0.3498. I have to put this in parentheses because I'm doing subtraction there. And then I'm going to be dividing by 0.9864. So that's an equation I'm going to need to put in, right? I'm going to solve for my concentration, and I'm going to use the absorbance values that I have here. So see if this makes sense. So this is going to be my concentration. So I'm going to solve for these concentrations in these unknowns. I'm going to create an equation. So it's going to be equal to my absorbance value. I need to put this in parentheses. My absorbance value minus 0.3498, and then divided by 0.9864. Okay? That is the concentration of protein in sample number 1 there, right? So now we're going to have, because this is going to be the same equation, this is where, again, Excel as a calculator really helps. If we just had one problem here, we could probably just do this on a piece of paper. But I'm just going to drag this concentration down here, and I'm going to get all of these values. Okay, so now these are the concentrations of protein that are within each of these unknown samples. Okay, so that was the next step that we have here. So we fit the data to a linear equation. We display the equation and the r² value. We set up the second data table and use the equation from above. It says, remember, use Excel as a calculator. Calculate the concentration of protein in each of the unknown samples listed in data table number 4. So next part here, it says, while it is generally not accepted practice to plot unknown values on a standard curve, do so and see if the data points fall where you'd expect. Okay, so what I'm going to show here is just we're going to create a second data series to plot on this same plot. So I just want to, as an exercise, show you how to do that, but then also sort of highlight that this is not what we typically do here. So because I don't want to sort of mess up the plot that I have here, I'm actually going to copy and paste this plot down here just so that I have the same plot that we're now going to kind of superimpose this other data. Okay, so again, I have my original standard curve. This is what a standard curve is supposed to look like. Now I'm going to take and superimpose this data on here. And again, not something that you normally do, but I want to show you that it behaves like we'd expect. Okay. So to do that, again, I'm going to control and click my chart here so that I can select data, and I'm going to add another data series. So to add another data series, you can see here's the original data series that's here. That's our absorbance value data. Why don't we go ahead? We can call this our standard curve. So that's going to be that data. And now I want to come down here. I want to say I'm going to add another data set. And I'm going to say this is going to be, we'll name this is my unknown data series. Okay. Again, I'm going to choose my X and my Y values. So my X values, again, X is always going to be my concentration. So that's going to be here. Okay. My Y values are going to be my absorbance values here. Okay. So I'm going to say okay. And look at what we see here. Again, this is not what you normally would do. You don't plot your data on your standard curve. So I want to make sure I say this like 12 times so nobody thinks that this is what you do. But this is just a proof of principle to indicate that's where we would expect our red data to be. Because we used this equation of the line to actually determine what the Y, use that Y value, that absorbance to figure out what my X was. These should all fall on the same line. Okay, so that is creating a standard curve, using the standard curve to kind of determine the concentration of protein in unknown samples. And again, just a proof of principle at the end here, just to highlight that all of these data points should fall on the same line because we use that equation to derive them. All right, a few questions then that you need to answer. We already talked about the y-intercept and why wouldn't we choose to set the y-intercept as something. Thinking about sample 8, right? So sample 8 was a sample that had no protein in it. So what's the significance of this? Could we use it for anything? And then it's just asking you to think about, let's assuming that the something that you could do with that value is to subtract it off of every single absorbance value. So I want you guys to think about how, if at all, it would change your plot, how, if at all, it would change your equation, change your r² value. Okay, so I'm going to leave those up for you guys to kind of think about, but that's creating and using a standard curve.